Hello, I've received several requests to go through the exam 4 review, so I'm going to do that and post it onto D2L. Here we have a question in which we're given a balanced reaction, and we're asked to and a starting point, which is in the box. And the question is, what must have been the products? Right, so we got to kind of go through what each of the particles are. So we go through A, we have 6 N2Os plus 9 H2Os. B, we have 4 N2s plus 2 oxygens plus 6 waters. Right, so we just account for all the particles that are there. C, we see you have 3 N2O, 6 H2O, 2 N2H4, NO3, and then D, we just have lots of particles, atoms, that we know is wrong. Okay, so the question is, can we have 9 waters? And the answer is no, because 6 N2Os would make a total of 12 waters. So we know A is wrong. B is wrong because N2 and O2 are not in the reaction. So, and D is lots of atoms, and so C is the right answer. You just want to make sure you know exactly why C is the right answer. And that's because to have 3 of the ammonium nitrates react, we would make 3 N2Os plus 6 waters. And that's exactly what we have, plus 2 unreacted ammonium nitrates. So that's consistent with the image shown. And of course, we excluded all the other answers, but it's really important to be able to predict this answer. Select all the ions below. Okay, so let's do that. Keep in mind our model for ionic behavior is a metal with a nonmetal. So that would exclude nitrogen and hydrogen, which is ammonia. That's not a metal. That's not an ion. Iron chloride is, iron's a metal, chloride is a nonmetal. Sulfur dioxide is not an ion because sulfur and oxygen are both nonmetals. Magnesium, 2+ sulfide, is a ion. Ammonia, or nitrogen with chlorine, again, 2 nonmetals, is not an ion. Iodine with chlorine is not a metal. Rubidium is a metal and would form a +1. It's in the first column. Rubidium iodide. Strontium is a metal, 2+ with oxygen. And then ammonium chloride is a metal. Keep in mind NH4+ is the polyatomic form NH4+ chloride. So yes, that would be an ion. So here we have you can quantify many of the changes in potential energy for the reaction in the forward and reverse direction and activation energies. So let's do that. So we put R and P here. So in the forward, R to P, we see the change in potential energy is positive 25 kilojoules per mole. It has an activation energy in the forward direction of 75 kilojoules per mole, and it's endothermic. In the reverse direction, going P to R, the change in activation energy is negative, meaning exothermic. Its activation energy in the reverse direction is a positive 50. Remember, the activation energies are always positive numbers. They're just different in the different directions. And let's see, so that means the answer here is C. The forward is endothermic and the reverse is exothermic, but we could extract all this information from this graph. All right, so here we have a chemical reaction. They're all gases, and it says, what would happen if we ran this experiment again, but in a bigger volume? Would we expect the rate of reaction to change, and if so, how? Well, remember, increasing the volume changes the concentration, right? The number of particles per unit volume that goes down. And so there's less collisions per second. So whenever we're looking at rate, we're thinking about the total number of collisions per second. And that always affects, so that answers D. It doesn't change the activation energy. It doesn't change collision effectiveness. It only changes the collision frequency. Since it decreases, the rate will decrease. Right, so N2 plus O2 reacts with NO, and then we want to know something about the activation energy and the configuration effectiveness. Right, to determine the configuration effectiveness, we have to write the balanced chemical reaction with their phases. And what we see is we have two gas particles reacting with two gas particles in both the forward and reverse direction. But the reactants are simpler, and the products are more complex. And so faster, remember the fastest direction based on configuration effectiveness is always 1, fewest gas particles. 2, if the gas particles are the same, then the simplest. And what we mean by simpler is that they have more of the same atom. So N2 and O2 each have only the same atom within their particles, so they're simpler than the NO particle, which has both an N and an O in each particle. So what that means is we'd expect the fastest direction to be the forward direction based on configuration effectiveness. Activation energy is much simpler. All we have to do is look at which direction would have the lowest activation energy. Here we see the forward activation energy is 520 kilojoules per mole. The reverse is only 520 minus 180, so which would only be 340. So we'd expect the reverse direction to be faster based on activation energy, but the forward faster based on configuration effectiveness. So we would pick B. So here we have an energy diagram. It says we want to increase the rate of the reaction. Remember, keep in mind this means increasing the rate. Always means increasing the number of collisions per second. That's what we want to do. Increasing the temperature will increase the number of collisions. Increasing the concentration will increase the number of collisions. So the answer is 1 and 3. Increasing the volume is not a good recipe for increasing the number of collisions per second. All right, balance a chemical reaction based on this data. Remember, keep in mind we do this in 3 steps. Step 1 is to account for all the particles, which we do that 6 carbons, 4 sulfurs, and 6 potassium nitrates, or KNO3s, and that makes 6 CO2s, 2 nitrogens. When we have 2 K2S's, that's coming up with the 2, and then 2 sulfurs in excess, 2 KNO3s in excess unreacted. Step 2, we're going to subtract the excess. So let's start doing that. So what we're going to do is we're going to subtract the sulfurs from both sides, the 2s, subtract the KNO3s from both sides. There's the 2. That should have been there. And that gives us, takes us to step 3, which is divide by a multiple, and they all share the multiple of 2. We divide by 2, and we get the final step, which is 3 carbons plus a sulfur plus KNO3. Make 3 carbon dioxides, 1 nitrogen, and K2S. Okay, so if you keep in mind these sequential steps, then all the problems you'll do will be pretty straightforward. Given this reaction, what acts as a limiting reactant? So we look at the carbon. So we're going to go through each of the reactants and see, are they present? Right? And you say, well, I don't see any free carbon atoms, but I certainly see excess sulfur, excess KNO3, so I would pick carbon. as the limiting reactant, meaning if we had more of it, we would make more product. All right, so we have a PEC diagram from Unit 3, Module 1. Keep in mind on the energy axis, which is the y-axis, the weakest interactions are on top. The strongest interactions are on the bottom, lowest potential energy. And that happens to be the undissolved case. And if that's undissolved, then it's the ion-ion interaction with water-water. That's the undissolved, those are the undissolved interactions. And those are the strongest. Here we're asked to pick which one's wrong. So we know, so the dissolved definitely has higher configurations. The ion-ion interactions are weaker. Well, that's false. The ion-ion interactions are stronger. That's true. And increasing the temperature will give us access to more dissolved, and that's true because it's at higher potential energy. So the best answer here for not being true, would be B. I didn't mark it, but it's the false one, B. Here we're given a chemical reaction of TNT. So we have this solid and it just explodes into a bunch of gas particles and other solid particles. And so what is true about this exothermic reaction? Well, keep in mind an exothermic reaction would look like this. It's always, the forward direction is always going to be faster because it has the lowest activation energy. So this is what's true about all exothermic reactions. The activation energy favors the forward direction. Now, configuration effectiveness here, we're making so many gas particles in the products, we definitely think that that direction is going to be slower because there's more gas particles. Whatever's fastest has the fewest number of gas particles. So we'd expect the forward direction to be faster based on activation energy, the reverse direction to be slower because it has so many more gas particles there. So we'd expect both A and C to be correct. All right, so here we have a submicroscopic representation. So let's go through all the options. A is a covalent, 1-to-1. So that would be like carbon monoxide. B is a covalent, 1-to-3. So that'd be like SO3. C is an ionic, 1 to, I guess it's 1 to 3. And D is ionic with 1-to-1. Calcium sulfide is 1-to-1, so we would pick D. Keep in mind A and B are assigned as covalent because, first of all, they're shown in what looks like a gas phase, and ionics are always solids. And also that they're shown as particles with their ratios, which is covalent behavior, not ionic. All right, so here we give another energy diagram, and it says we want to know, would this be a good explosive? So what are good explosives here? You say, well, explosions usually release energy, and this one's endothermic, so this is taking in energy. So this is not a good chemical explosive as heat's absorbed. So we would pick, B because it's not exothermic. And exothermic is what we'd expect an explosion to do, which is release energy to its surroundings. All right, here we have a chemical reaction. It says highly exothermic. Okay, so it's highly exothermic. Which energy diagram would this correspond to? This would be D because this is where we have the high potential energy to low potential energy, releasing energy. A is endothermic, B is endothermic, and C is showing no change. So the answer is D, exothermic. We're given a box with some products and told what the reactants species are. So we see N2 has to react with H2 to make N2H4, but that's not balanced because we got to put a 2 there. So that immediately answers the question. The answer is B. But we also can see what must have been in that box to give us those products. And so we see if we had 2 N2H4s made, we must have had 2 N2s and 4 H2s. So we put those in the box. That's what must have been there to make those 2 product particles. Then we have 2 particles that were unreacted that are present. So we put those in there. And that tells us that in the box, we must have had 3N2 plus 5H2 to make what was present in the red box given. We've balanced the reaction, and that answer is B, but there are other questions in the activity and in the review that ask you for what particles must have been there, and that's how you would do it. Okay, so here's some quantitative problems coming up. So how many molecules of NO will be produced for every 100 molecules of HNO2? All right, so what we see from the chemical reaction is 2 molecules of HNO2 make 1 molecule of NO. And what we find is we have 100 molecules of HNO2, so how many molecules of NO are made? So that's one way to do it. That's the ratio method. And solving for x, we see the answer is 50. Could also do this using more traditional methods, but it's a little bit cumbersome. It's 100 molecules of HNO2. For every 1 molecule of NO, you need 2 molecules of NO2, and you still get 50. So either way, the answer is 50. Here we want to know which of these answers, so just kind of ignore the A, B, C, D here. Which of these substances would be expected to be soluble in water? Right, so solubility, we first assign all the charges. So the Q1 times Q2 of zinc sulfide is -4. Potassium and nitrate is -1. Iron oxide, Fe3O4, is going to be +3. Actually, this one's, well, we're going to put +3 -2 for now. It's actually a little bit more complicated than that because there's 2 different iron in there, but in general it's just let's say it's -6. Iron sulfide is -4, but the main thing here is the only one that would be expected to be soluble is potassium nitrate with a -1. We'd expect all substances with Q1 times Q2 -4, -6, -8 to all be insoluble in water. Okay, so here we have a configuration effective problem. We want to know in which direction are these reactions going fastest and to select which one has the forward going fastest. Okay, so we have we have 3 gas particles going to 2 gas particles in the forward direction, and in B we have 1 gas particle going to 0 gas particles in the forward direction. In the reverse direction, we'd have 2 gas particles making 3 gas particles, and in B, we'd have 0 gas particles making 1 gas particles in the reverse direction. So what we see is, in both cases, the reverse direction is going to be faster because there's fewer gas particles making more gas particles in the reverse direction. So the fewest gas particles are always going to react faster. They're always going to be the ones that are favored by configuration effectiveness, meaning faster. So the answer is neither, since the reverse direction is going faster in both cases. How many molecules of NO2 will be produced for every 100 molecules of HNO2? It looks like we have a repeater here. So I'll just skip that. We did that already. The answer is 50. All right, so let's rank some potential energies. So first, again, we have to determine the charges. So aluminum oxide, Q1 times Q2 is -6. Zinc sulfide, Q1 times Q2 is -4. And iron oxide is Q1 times Q2 is -6. So for ranking potential energies, we see that the Q1 times Q2 is definitely proportional to potential energy here. So the -4 zinc sulfide is the least stable, highest potential energy. Then we have aluminum oxide and iron oxide, both at -6. If remember, the biggest one is going to be the least stable, the smallest one the most stable. And so we'd pick iron to be the one that is biggest. And you say, why is that? Because it's a row 3, and aluminum is only row 2. And then remember, potential energy is proportional to Q1 over Q2, product over R squared. So that's our formula. And so when we multiply the charges, we see that the potential energy definitely goes down. This is the same, would be the same for the melting point. We'd expect zinc sulfide to have the lowest melting point and aluminum oxide to be the highest melting point. All right, so here we have some information. We're given information by looking at the photoelectron spectrum. So if we did the electron configuration here, we see A is calcium. And we know calcium forms 2+ because it has 2 electrons in the outer shell, which are very reactive. And in the ionic case, we would have that. B is 1s2, 2s2, 2p5. That's fluorine. And we know fluorine takes on an extra electron because there's only 7 in its valence shell to become 8, which is fluoride. Calcium fluoride would then form CaF2. So remember, the metals will always lose the number of electrons to achieve the valence shell of the noble gas. Calcium 2+, fluorine accepts an electron, those electrons, and becomes fluoride. Okay, this is a limiting reagent question. All right, so we have 10 grams of each. So the first thing we have to do is balance the reaction. We have HNO2 plus O2 to make HNO3. We put a half there on oxygen, but we don't like to do that, so we multiply everything by 2, and we get this result. All right, so now we could do this 2 ways, right? Okay, I think we're back. Had a little problem there. Okay, so then we are going to do this 2 ways. We can do the ratio method by putting in the masses that react in the chemical reaction. We'll also do the grams per moles method also. Okay, so using the ratio method, what we see is that 32 grams of oxygen make 126 grams of product. Right, do we have 32 grams? No, we only have 10 grams. So we want to know how many grams would be made here. And we solve for x, and we see the answer is 39.4. So the maximum 10 grams of oxygen can make is 39.4 grams of product. Do the same thing for HNO2, 94 grams of HNO2. The maximum it can make, so it can make 126 grams of HNO3. We don't have 94 grams, we only have 10 grams, so Y grams. How much does 10 grams make? And if we do that, we see we only have 13.4 grams of product. Right, so that means that the limiting reactant must be HNO2 because it makes the least product. All right, so let's take a look at doing this in the grams to moles to grams method. So we start off with 10 grams of oxygen, and we convert to moles, right, step 1. Then next what we want to do is use the chemical formula ratios, mole ratios, to connect to how much product we would make. So there's 2 moles of HNO3 for every 1 mole of oxygen. Then we convert to grams of HNO3, And if we do that, we get 39.4 grams of HNO3 made. If we do 10 grams of HNO2, do the same thing, convert to moles. Now we have 2 moles of HNO3 for every 2 moles of HNO2. And we convert again to grams, same step as above, and we get 13.4 grams. So same result, same answer, which is that HNO2 is the limiting reactant. 2 different methods. It just depends on how comfortable, whichever one you feel most comfortable with. But both of them are available to do any problem on the test since it's multiple choice. And all right, next. If 92 grams of NO2 was produced, how many grams of HNO2 must have been present? All right. Okay, so we can just set up the ratio method quickly. 46 grams of NO2 make 94 grams, or have come from 94 grams of HNO2. We don't have 46 grams of NO2. We have 92 grams of NO2. So how much must have been there? Right. So and it's 94 grams. Right. So solving for x, we see that we must have had 188 grams of HNO2 to produce the 92 grams of NO2. Okay, so we can also do this in the grams to moles method. Again, just however you want to do it. So 92 grams of NO2. First convert to moles of NO2. Now link it to the product you're interested in. We're actually interested in a reactant, but we relate it by moles. So 2 moles of HNO2 for every 1 mole of NO2. Then we convert to grams of what we wanted, and we get 108 grams. So the same answer, just make sure you can obtain it, whichever method you use. All right, if 15 grams of NO was produced, how many grams of HNO2 was present? Okay, so it's basically the same thing. We put up our grams for the ratio method. So 30 grams of NO is made from 94 grams of HNO2. We only have 15 grams of NO, so how many grams of NO2 do we have? And we see we have 47. Putting this in the grams to moles method, convert to moles, convert to the item given, and then convert to grams. We do that, and we get the same answer, 47 grams. All right, so which of the statements are correct here? Well, it's definitely not a forward direction endothermic. It's forward exo. It has a positive activation energy in the forward direction, and it has a positive activation in the reverse. It never has a negative activation energy. And the activation energy in the reverse direction is larger. Absolutely true. So this is always positive, the activation energies. And the activation energy in the reverse direction is larger than the forward. That's true. That's true for all exothermic reactions. So 3 answers here. All right, and calculate the activation energy for the reverse direction. We did that in the previous problem, but the forward reaction is 520. Reverse, since the potential energies are already higher in the products, we'd subtract it and we get 340 kilojoules. All right, that's the exam 4 review. Good luck.